Alright, so we have already learned that a system of linear equations can be written in matrix form. And in matrix form, we can perform the operations that we use in Gaussian elimination, and we call them our elementary row operations. However, we still need one thing. In Gaussian elimination, our goal is to write the system in row-echelon form so that we can perform back substitution. This would mean that in matrices, we can also write a matrix specifically in row-echelon form. And how do we have that? So a matrix in row-echelon form has the following properties. 1. Any row consisting entirely of zeros occur at the bottom of the matrix. So say we have here matrix A. This is the name of the matrix, matrix A. No row entirely of zeros, so we will not have anything here at the bottom, but in case there are, it should be at the bottom. For each row that does not consist entirely of zeros, the first non-zero entry is 1, and we call that the leading one. So as you can see here, the first non-zero entry is 1. Here it's also 1, and here the first non-zero entry, because the rest are zeros, are 1. And finally, for two successive non-zero rows, the leading one in the higher row is farther to the is farther to the left than the leading one in the lower row. So this is the leading one in the second row, and the leading one in the first should be farther to the left so that it will be row-echelon form. And similarly, the leading one here in the third, in relation to the leading one of the second row, this one should be farther to the left of the leading one of the third row. So now that we have checked all of these, we can say that this matrix A is in row-echelon form. So therefore, with that, let's try to determine if these matrices are in row-echelon form. Pause the video and try to see whether the following matrices are in row-echelon form. Alright, so let's check our first matrix. So a row of zeros, there's none. Then we have our first non-zero are all ones, then all leading ones. The highest leading one is farther to the left. This is farther to the left than this one. So therefore, this is in row-echelon form, or REF. How about the second one? So the second one here, this is our first non-zero, it's 1. Our first non-zero is 1, first non-zero is 1, and first non-zero is 1 as well. This is farther to the left than this one. This is farther to the left than this one. And this one is farther to the left than this one. So we can also say that this is also in row-echelon form. Finally, in the third one, we don't have any zero rows, but we have a leading that is not 1. Not 1. So therefore, this is not in row-echelon form that I have been writing as REF. And now, we already have the elements that we would need to perform Gaussian elimination if we would write our system in matrix form. So, if you would recall, we wrote our system in matrix form, especially an augmented matrix. Then we learned about the different elementary row operations that are very similar to the operations that we use in Gaussian elimination when we have equations. And finally, we already learned how to write an equation in row-echelon form. So now we are ready to perform Gaussian elimination using matrices. So here are the steps. First, we write the augmented matrix of the system of linear equations. Then we use elementary row operations to rewrite the matrix in row-echelon form. And then write the system of linear equations corresponding to the matrix in row-echelon form and use back substitution to find the solution. So we're going to show an example of Gaussian elimination using matrices using these systems in the next video.